Hi guys, Terry here. In this video, I'm going to be going through the solutions to the June 2023 paper 2, right? Guys, just remember to hit like and please hit subscribe if you like the work that I do online. So overall, this paper was pretty straightforward, right? Figure 1 shows the setup of an experiment to determine the specific heat capacity of 300 grams of a liquid using an electrical heater. The heater has a power rating of 105 watts. So they give us a diagram here. We have a thermometer inside this liquid, and we have a coil that is heating up the liquid first, right? They gave us information regarding temperature and time for the liquid, right, in a polystyrene foam cup, right? So we have temperature, we have time in seconds. Right, so the first thing here, they want us to define specific heat capacity, right? So this is the energy required right, to raise the temperature of 1 kilogram of a substance by 1 degree, right? And that 1 degree could be in degrees Celsius or degree Kelvin, right? So that's the definition here. Energy required to raise the temperature of 1 kilogram of a substance by 1 degree. Now, assuming that all electrical energy produced by the heater is transferred to the liquid, right? So P is electrical power of the heater, T is the time duration for the experiment, M is the mass of the liquid, C is the specific heat capacity, and delta theta is the increase in temperature. Deduce the formula which represents the heat energy transferred from the heater to the liquid. Well, the energy transferred by the heater is power by time, and the energy absorbed by the liquid is going to be mc delta theta, right? So 1 mark just for writing that there. Use the grid provided on page 7 to plot a graph of temperature versus time, right? So for 8 marks, we have to draw a graph, and we have to use the data that they gave us here, right? Let's see. Let me pull this table across. All right, so this is my data here, right? Let's see what graph they asked to plot. Okay, so they told us temperature versus time. So always remember the first variable is going to be your y variable, and time here is going to be your x variable, right? So beforehand, you should know what you're going to plot. So y is temperature. So this is y here, and this is x, right? Now, so we should label our axes one time, right? So on your x-axis, we have time. So you're getting marks for labeling the axes properly, right? So time in seconds. Across here, we're going to have temperature, right? And that temperature there is in degrees Celsius, right? Now we want to plot this here. So we need to look at the data itself. So on the x-axis, your smallest value is 0, and we're going up to 360 here, right? So we need to select an appropriate scale. Now let's see what scale can I use here. 10, right, so based on the numbers I'm seeing here, right, what could probably fit, because I need to get up to 360, I can probably go, and if you look at the time, it's increasing by 60 every time. So we could probably do 60, 120, right, then 180, right, and then we can go 240. I generally don't like a scale like this, but because the time intervals are increasing by equal amounts of 60, we can go ahead and do that. Right, so that's 240. This here is going to be 300, and then the last one here is going to be 360, right? So that's going to be my scale here. I'm going to use 2 cm, right? 2 cm to represent 60 seconds, right? Then on the y-axis, I can probably, how far are we going up? Lowest value is 25.3, highest value is 56.8. So maybe I can go 10, 20, 30, 40, 50, 60. Right? I guess I could probably, that might be the best scale I could probably use there, right? So that's my temperature axis here, right? Now to plot the points, the first one is 0 against 25.3. So 25.3 is probably somewhere here, right? So that's the first point. The next one is 60 against 30.5. 60 against 30.5 is somewhere here. Right, next one is 120 against 34.9. 35, 34.9 is probably around here. Next one is 180 against 41.2. It's 41.2 is somewhere here. Right, next one is 240 against 46.4. Right, next one is 300 against 51.5. That's about here. And the last one is 360 against 56.8. So this is 55, 56, 56.8 is probably around here. Right? So those are my points that are plotted there. And we can see that we have a general straight line here. So the next thing you have to do is to take a long transparent ruler, right? So I always tell my students, make sure and walk with a clear transparent ruler. Not that one from the geometry set, but a long one, right? Not those long wooden ones. So what we have to do here is to draw our line of best fit. Now when you're drawing a line of best fit, you try to draw your points so that they kind of fit on the line, right? You kind of balance the points if they all don't lie in the same straight line. But the second point, let me double check that second point, 60 against 30. 60 against 30.5, 120 against 34.9. 34.9. All right, so this one point here seems to be a little off, but all the other points lie on the same straight line. So I'm going to go with that as my graph, right? So 8 marks for that. So you're getting marks for selecting the appropriate scale, plotting the points accurately, labeling your axes, right? And you can also say, you're not getting marks for this, right? But graph of temperature, right, versus time, right? And that's exactly what they told us to plot. So the next part now, calculate the gradient of the line. So everybody should know by now, once we have a straight line, they're going to ask us to find gradient. So it's going to be y2 minus y1 over x2 minus x1, right? So we're going to select any 2 points, right? Any 2 points from the graph. And that's totally up to you. Right? Now, what I'm going to do here though, I'm going to select points that lie on my straight line. This first point here lies on a straight line, and I can probably use, right? Let's see. Trying to figure out if to use a point on my line or if it's easier to select any other point, right? You know what? I'm going to select a point, 2 points that I did not plot, right? I'm going to select 2 points that I did not plot. So the first point that I'm going to do, I'm going to select 30, and that's 30 against 28, right? This point here, right, is 30, 28, right? Let me call this point E. And the second point that I'm going to choose here is 330. Let's call that point B here, right? Now in the exam, what they normally expect us to do is to draw or complete a right angle triangle to show them exactly what we're using to get the graph, to get the gradient, right? So hold on a sec. Right? So what you will see sometimes, they will tell us to complete a right angle triangle, right? So I'm just using the points A and B that I have selected, right? Now keep in mind that it doesn't matter what points you use, right? The rule of thumb is that we have to select 2 points that are in such a way that they're about more than half the length of the line, right? I don't think you all might see this properly, so let me just increase this thickness a little bit. Right? So those are my points that I'm going to use to work out my gradient. So I'm just going to write down what is A. So the coordinates of A will be 30, 28. So A is 30, 28, and B is, what is B here? B is 330, 14, sorry, 330, 54. 330, 54. Right? So what I normally tell my students to do, always label this. So you're going to label this as x1, y1, label this as x2, y2, right? So now it's just a matter of substituting into your formula here, right, for gradient. So y2 is going to be 54 minus 28 all over 330 minus 30. So that's going to give me 54 minus 28 divided by 300, and I'm getting about 0.0867, right? Right, now remember your answer is going to vary depending on what points you selected, right? Now since we plotted temperature, right, which is in degrees Celsius, against time, which is in seconds, your unit here is going to be degrees Celsius per second, right? So like I said, this number here, right, is going to vary depending on the points you select, right? Now let me just double check something here. I want to see. Minus 25.3 divided by 360. Yeah, it's probably around that, right? Because I use the two endpoints and I'm getting 0.0875. Yeah, so it's gonna vary a little bit, right? What else they want now? So given that G is equal to P over MC, right? Calculate the specific heat capacity of this liquid here. So G is equal to P over MC, right? So therefore, if I cross multiply, I'm gonna get MC multiplied by G is equal to P. So therefore, C is equal to P over M multiplied by G, right? So my power, they told you the power of the heater in the beginning somewhere. It's 105 watts. Right? So it's 105 over what it told us is the mass. So the mass is 300 grams, right? But I'm going to work in kilograms. You don't have to, right? So you can put 300 or you can put 0.3 kilograms, right? Multiplied by the gradient that I just got there, which was 0.0867. 0.0867. And we're just going to find the value of this. So 1 over 5 divided by, open brackets, 0.3 multiplied by 0.0867, right? And I'm getting around 4037, right? Now this is specific heat capacity, so it's going to be joule per kilogram, because I converted mine to kilogram, per degree Celsius. Right? So 6 marks for this, but remember you have to give your units in order to get the marks, right? Right? So that's my specific heat capacity, right? Your answer is going to vary based on your gradient, though, right? Right. So the table shows specific heat capacity of 3 commonly used liquids. We have cooking oil, we have milk, we have paraffin, right? Using your answer calculated in C part 1, state the liquid most likely. So we got a value of 4037, right? So it's a good thing we worked in kilograms, because right? So we got this joule per kilogram per degree Celsius, right? Now this is the value that we got, and it's a good thing that we worked in kilograms, because they gave us a table, and they gave us a table in kilograms here, right? Now the only number that is close to 4037 is this, right? The other two numbers, like cooking oil and paraffin, they are much lower, right? So that liquid that we have here is most likely milk, right? So 1 mark for that. state one precaution that the class should take in performing this experiment. Now, this is an experiment involving heat, right? Involving heat. Yeah, so once you're doing an experiment like this, right? Now, you're already using a polystyrene foam cup, right? So therefore, you're already trying to insulate the milk here, right? So therefore, you're already trying to assume that all the energy supplied is equal to the energy gained by the milk, right? So we can't go and say that here. In this case here, what needs to happen, right? You have a heating coil and stirrer, right? So you have to look at precautions in terms of electrical safety, right? You're dealing with something that is hot, so you have to be careful not to touch the hot object, right? Like the heater or anything like that, right? So let me see something here. So state one precaution, right? If you look at the diagram itself, right? You want the thermometer not to be touching the sides of the polystyrene foam cup, right? You need to ensure that the thermometer is in the milk itself, right? Don't touch the heating coil, right? You're using an electrical appliance here, right? You have to make sure that there's no breaks in the wires, right? So those are safety precautions that we should consider when we're looking at this here, right? So 1 mark for this. So any one valid precaution is going to work, right? Let's move on to question 2. So question 2 here shows a wind turbine used in the Caribbean, in some Caribbean countries, as an alternative source of energy. Describe how the wind turbine produces electrical energy. So this is 3 marks here, right? So basically, we have to say that the wind, right? So basically, wind blows this thing. So the wind turns the blades, right? The blades turns a shaft. Blades turn a shaft, right? Which is connected to a turbine, right? And we just need to say that the turbine, right, converts kinetic energy into electrical energy. Right, so that's what's happening here, right? So the wind blows the turbine. The wind blows the propellers. Propellers turn. The propellers turn a shaft, and the shaft is connected to a turbine. So the turbine is basically converting kinetic energy into electrical energy, right? So that's pretty straightforward. So the wind blowing here, and it causing this thing to turn. That's it, right? Next one. State 2 advantages and 2 disadvantages of using wind turbines in the Caribbean. So we have wind turbines, right? So advantages, right? We are Caribbean islands for the most part, right? So we have abundance of wind energy, right? So there is an abundance right, or availability of wind. So that's our most obvious answer that we should have put, right? Just like how we have a lot of sunlight in the Caribbean, so solar is a good option in the Caribbean as well. Yeah, so abundance or availability of wind. Next thing here is that there are no pollutants, right? There are no pollutants. Yeah, so we have no pollutants, right? And when I say no pollutant, I mean like CO2, right? There's no greenhouse gases being produced in this whole process, right? So it's a clean form of energy, right? It's a clean form of energy, right? And you can also say that it is a renewable source of energy as well, right? Right, so they just want 2 advantages. So any 2 valid advantages is going to work, right? What are the disadvantages, right? So in terms of disadvantages, one, it takes up land space, right? But it's not just a matter of taking up the land space, right? This land space could have been used to plant food, right? So it takes up land space, right? So it affects housing and agriculture, right? And agriculture. So we live on islands here, so I mean we kind of have to manage our land use properly, right? So it takes up land space. Another disadvantage is that they kill birds, right? Wind energy, right? They kill birds. So you have birds flying there and they end up crashing into the propeller blades, right? Yeah, so they kill birds, right? What else do we have here? Right, another disadvantage is that wind, right, is variable, right? Meaning that the wind is not going to blow all the time, right? It's not going to blow all the time. So what you have to do is that when you generate the power, you're going to have to store the energy in batteries, right? And that could also be costly, right? Another thing is you can look at the aesthetics of this thing. Nobody wants to see a set of windmills in their area, right? So there are several disadvantages, right? But they just want two, any two will work. If the mass of air that passes through a circular area swept out by the turbine blades every second is 8.5 kg, kinetic energy at this time is 2500. Calculate the speed of the air, right? So we're using our kinetic energy is equal to a half mv squared, right? So all we need to do is to rearrange this formula. So we have 2 multiplied by ek, right, is equal to mv squared. So we can say that mv squared is equal to 2 multiplied by your kinetic energy. So therefore, v squared is equal to 2 multiplied by ek over m. So therefore, v is equal to the square root of 2 by ek over m, right? So I'm just working out the formula first before I make my substitution. So this is going to be 2 multiplied by the kinetic energy, which is 2500, over the mass, which is 8.5. And you have to find the square root of this, right? And that's going to be 2 by 2500 divided by 8.5, second function, square root. And that's going to give me about 24.3. Yeah, 24.3 meters per second, right? Let me just double check this. Squared multiplied by 0.5. Yeah, okay. So that's the speed there that they're looking for. That's it. Next part, they want the input power of the air, right? What is the input power of the air, right? Now remember, power, right, is given by energy over time, right? Now the energy, if we read what they said here, they said the kinetic energy during this time is 2500, right? Now if you read the question, they spoke about every second, right? So this is every second that they're talking about here. So all you need to do is to take the 2500, right, divided by 1 second. So you're going to get 2500, but you need to give the correct unit. So it's going to be watts. So it's 2500 watts. That's the input power into this thing here. The second thing here, they want the efficiency of the turbine. So you need to know that efficiency is equal to power output over power input multiplied by 100%. Right? Your power output, they said the output of the generator is 1350 over the power input, which was 2500 multiplied by 100%. Right? And in this case here, it's going to be 1350 divided by 2500, and you're going to get about 54% efficiency, right? You're getting about 54% efficiency. All right, next thing here now. So this is the third question. State 2 properties of EM waves or electromagnetic waves, right? So what we can say is that they are transverse, right? So all EM waves are transverse waves. They travel at 3 by 10 to the 8 meters per second in a vacuum. Right? Now they said two properties, right? So I have two here, right? But you can also say things like they can be reflected, right? Refracted, right? Diffracted. Right? And show interference. Right? So that's the answer for that part here, right? Next part here, it shows a cup and a string telephone. Describe how the cup and the string telephone works. Right. Now, basically, let's say this person on the left here is talking, right? What's going to happen here is that from their mouth, you have a sound wave being produced, right? Now that sound wave there is going to cause the cup to vibrate, right? And this vibration passes along the string. It reaches the other cup, right? And that cup is going to vibrate at that end as well. So there are certain terms that they'll probably be looking for in your answer here, right? So sound wave, right, causes one cup to vibrate, right? Now, you need to mention the word longitudinal wave somewhere inside here, right? So even though the cup is vibrating, right, that sound wave itself is moving along the string. So the sound wave causes one cup to vibrate, right? This vibration, right? And what I would put here, I would put in brackets longitudinal wave, right? And I should probably put longitudinal progressive wave to be a little more precise, right? So the vibration, right, travels along the string, right, and reaches the other cup. Right? Right, so it reaches the other cup, right? And what happens here is that the other cup, right, vibrates and produces, right, a sound wave at the other end. Right, so any explanation that kind of says exactly what's happening here, right? But the key words that you probably need to say here would be longitudinal wave, right? You probably need to say progressive, right? And another key point that you could probably mention here is that sound waves require a material medium to be transmitted. Right? So that's part B. Right? Next part here, calculate the wavelength of the sound produced by the cup and the string telephone given at the frequency. So we have frequency is 11,000 hertz, right? The speed of sound, so V is equal to 330 meters per second. We want the wavelength, right? So you're going to use the formula V is equal to F by lambda, right? So wavelength is equal to V over F, So the speed here is 330 divided by 11,000. Right, and we're going to get 0.03. Right, and that is wavelength, so that's meters. Right, so 3 marks for that. Next part here now. Figure 5 shows a coin at a position O in an empty container. An observer is unable to see the coin based on the position of the eye. Right, obviously, because light travels in a straight line. So if light is bouncing off the coin, right, if your eye is positioned here, you're not going to see the coin at all. Describe how the observer can see the coin when the container is filled with water. Well, if the container is filled with water, what's going to happen is this. A ray of light, let's say a ray of light were to do this, right, coming out here, right? Because you're traveling from water to air, you're going to have refraction taking place. So as soon as this ray hits here, what's going to happen is that it is going to bend, right? The ray is going to bend, right? So if it bends, there's a good chance that you can see the object now, right? So they said for 2 marks, right? So when the container, when filled with water, right, rays of light, right, bouncing off the coin, right, because the coin is not producing light. Coin is not producing light. The reason why we see it is because light is being reflected off of the coin, right? So when filled with water, the rays of light bouncing off the coin, right, refracts, right? So when we say refracts, it's going to bend, right? Refracts when traveling from water to air, right? And the ray enters the eye. So the rays, or the ray enters the eye. Right, this is only 2 marks. So the key thing that they're looking for here is really refraction, right? Next part here. The refractive index of water is defined as the speed of light in air to the speed of light in water. Calculate the speed of light in water given that the speed of light in air. Okay, so refractive index is given by V1 over V2, right? So 1.3 is equal to V1, which is the speed of light in air, which is 3 by 10 to the 8 over V2, right, which is the speed in water. So we're going to write this as 1.3 over 1, and then you're just going to cross multiply. So 1.3 multiplied by V2 is equal to 3 by 10 to the 8. So therefore V2 is equal to 3 by 10 to the 8 over 1.3, and that's going to give me about 2.3 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8. So 2.3 by 10 to the 8 meters per second, right? So that's the answer there for that part. And the last part, we want the critical angle for water. So critical angle N is 1 over sine C. All right. Or we could, let me just write it the next way. All right. Sine C is equal to 1 over N, right? So sine C is equal to, the critical angle is 1.3, I think they said. Yeah, 1.3. So this is 1 over 1.3. So therefore C is equal to arc sine 1 over 1.3. So therefore C is equal to and again about 50.3 degrees. Right? So that's my critical angle there for water. Right? Alright, so that is question, the third question, right? So guys, just hit like and please subscribe. Right, a lot of students use my resources and they are not actually subscribers. So please just give me a thumbs up, right, and hit subscribe, please. All right, so let's see what else here. So some students complain that they didn't know how to draw this, right? I know I would have done this with my online Form 5 class on more than one occasion. So draw a label diagram of the structure of a thermocouple, right? So basically we have a sensitive galvanometer or a voltmeter, right? And we're gonna have two separate wires, right? So a thermocouple has two junctions, right? Right, now the thing is for 3 marks here, you need two different metals, right? So if you couldn't remember the metal, you could have called this metal X, right? And this here is also metal X, right? And then we have a different metal here. This one here is metal Y, right? So if you couldn't remember any of the metals, that's fine, right? But it's basically two different metals and they're connected. You have two junctions, right? This junction here is our cold junction, right? So that might be an ice water or something like that. And this here is the probe that we're going to use to measure our temperature, right? That's what we're going to use. It's a small tiny probe that you're going to use to measure your temperature. So this is the simple diagram here that you need for a thermocouple. A thermocouple is used to measure the temperature of the blue part of the flame of a small candle, right? So let's take a look at this here. So you have a flame here, right? And you're going to take this. Now the flame has different colors, right? Meaning that we have different temperatures in the flame. So the thermocouple, right? You're going to insert the thermocouple here, the probe, and you're going to measure the temperature. So there are 3 reasons why the thermocouple is suitable for this application. So one, right? The small junction, right? Right, is able to be inserted in the blue part of the flame. Right, so because the thermocouple itself is very small, you can actually take the probe and actually stick the probe directly into the blue part of the flame. Right, so the small junction is able to be inserted into the blue part of the flame. Right, so that's one. Right, the second thing is this. Right, the thermocouple, right, one of the biggest advantages of a thermocouple is that it can respond to rapidly changing temperatures, right? So it responds, right, quickly to rapidly changing temperatures. Right, so that's what that is the main advantage of a thermocouple, right? So I would have included this here as part of an answer, right? They want a third one, right? So we can say something like, if you couldn't remember anything, you could say very accurate, right? So they're very accurate, and also, right, they can measure very high temperatures, right? So they can measure very high temperatures. Right, so that makes it very suitable for measuring a flame, right, the temperature of a flame. So any 3 reasons here and you're good to go. What else we have here now? Figure 6 shows a mass of a gas that is trapped in a cylinder by a piston, right? The gas is at an atmospheric pressure of 1 by 10 to the 5. The volume of the gas is 1.9 by 10 to the minus 4. Right, so the electrical heater is used to increase the temperature of the trapped gas to a final temperature of 627. All right, let's see what they want here. Use the kinetic theory to explain how the gas exerts a pressure on the piston. So I've done this like a million times online as well as in my classes. So there are certain key things that they're looking for here, right? So the gas particles, right, are moving randomly in all directions, right? Now they collide with each other, but the key thing here is that they collide with the walls of the container. So they collide with the walls of the container. Right? So they collide with the walls of the container. That is true, right? Now the thing is, because they collide with the walls of the container, there is a change in momentum, right? So they undergo a change in momentum. And if you all remember, a change in momentum is what causes a force. So they undergo a change in momentum and therefore exert a force on the walls of the container, right? And they exert a pressure, right? Because a force is exerted over an area, right? So you can write the formula: pressure is F over E. That's essentially what's happening here, right? Particles collide with the walls of the container. There's a change in momentum, therefore a force is exerted. This force is being exerted on the inner walls of the container, so therefore pressure is equal to force over area, right? Calculate the final volume of the gas. Calculate the final volume of the gas given that the final pressure is that. So let's go back to the question here. What's happening here? Everything changing. We know pressure, volume, and temperature. All right, so this one we're going to use the combined gas law here, right? So P1 V1 over T1 is equal to P2 V2 over T2, right? Now let's look at all the information they have. The initial pressure is 1 by 10 to the 5. So this is 1 by 10 to the 5 multiplied by the initial volume. What is the initial volume? 1.9 by 10 to the minus 4. 1.9 by 10 to the minus 4 all over your initial temperature. Now, the thing is, and I always tell my students this, right? When you're doing the gas laws, you got to make sure and convert your temperatures into Kelvin. So if you didn't do that, that's a problem. So 27 degrees, if you convert that, you're going to say 27 plus 273, right? And that's going to give you 300 Kelvin, right? So you have to do that conversion. If you don't, you're going to get wrong. So it's 300 Kelvin here, all over P2. What is P2? Oh, right. So the final pressure here is this: 1.8 by 10 to the 5, right? Multiplied by volume, which we don't know, that's V2, all over your final temperature, which was 627, right? 627, again, you have to convert that 627 to Kelvin. So 627 degrees Celsius, right? We're going to have to add, so 627 plus 273. You're going to get 900 Kelvin, right? So basically, we double in the temperature here, right? Now, this is a key step, guys. If you forget this, you're going to get the calculation wrong. That's why it's 6 marks. So V2, I'm just going to cross multiply one time. So it's going to be 1.5 by 10 to the 5, multiply by 1.9 by 10 to the minus 4, multiply by 900, all over 1.8 by 10 to the 5 multiplied by 300, right? So therefore V2 is equal to, so let's check this properly, right? 1 by 10 to the 5 multiplied by 1.9 by 10 to the minus 4 multiplied by 900 divided by open brackets 1.8 by 10 to the 5 multiplied by 300. And I am getting my final volume as 3.17 by 10 to the 1, 2, 3, 4. So this is minus 4 meter cube. Right, so that takes care of question 4. Let's see what they have as question 5, right? Question 5, state the name of the logic gate, right? So this here is what we call a NAND gate, right? Based on the diagram, it's a NAND gate. Say the name of the logic gate using the truth table. So if you look here, the input, if you enter 0, 1 comes out. If you enter 1, 0 comes out. So this is a NOT gate. This is an inversion taking place. So it's a NOT gate. Right? So if I were you guys, I would have loved a question like this in my exam, right? So they want us to complete the truth table. So you have two inputs, A and B. So you need to count in binary here. So 0, 0, 0, 1, 1, 0, and 1, 1. That's what you're going to do, right? Now you're going to treat each one. So if you look at the output C here, you're passing through an OR gate. So an OR gate, you will only get an output of 1 when you have a 1 or something else, right? So you'll get a 1 here, a 1 here, a 1 here, and this is going to be a 0. In the case of D now, right, you're going to invert whatever is at B. So therefore, this is going to be 1, 0, 1, 0. So we inverted the output there. Now, the next thing here now, we need to work out what's happening at E. Now, this here is a NAND gate, right, which is the opposite of an AND gate, right? And the inputs we need to look at C and we need to look at D here, right? Now, for an AND gate, you only get an output of 1 when you have a 1 and a 1, right? So therefore, because it's a NAND gate, this has to be 0. This is going to be 1, 1, and this is going to be 1 here, right? And then the final output Z, right? You have to look at, now this is, I got to be careful here. You're looking at C and you're looking at E now, right? And you're passing it through an OR gate. If you're passing it through an OR gate, a 1 or anything is going to give you a 1. So therefore, this will be a 1, this will be a 1, this will be a 0. Sorry, it's not 0. This is a 1 as well. This is a 1. Yeah, that's a 1. And everything seems to be 1, right? Right? So that's a strange question though. Everything is, the output is 1, right? Okay. Part B now. What we have here, the arrangement shows diagram shows the arrangement for making an electromagnet. So we have a coil, right? We have a 12-volt supply, a meter, a variable resistor, and a switch. Say the material which is suitable for the core of the electromagnet. So the answer they're looking for here is soft iron, right? That's the answer. List 2 factors which would cause an increase in the strength of the electromagnet. Well, if you want to increase the strength of the electromagnet, right, what you can do is to adjust the variable resistor so that we have more current, so we can increase the current. The current in the coil. As one option, right? Another option here is that we can increase the number of turns in the coil, right? So increase the number of turns in the coil, right? But that's it. That's what I would say, right? Because there is a formula, right, that determines your magnetic field. You all don't need to know the formula, but the formula is this, right? Mu Ni, right? So it depends on the number of turns. It depends on the material itself. We're already using soft iron, right? And it also depends on the current, right? State how the component X can be used to increase the strength of the electromagnet. What is X here? Oh, X is the variable resistor. So this here is your variable resistor. Right? How can that increase the strength of the magnet? Well, all you need to do is to adjust it so you're reducing the value, right? So you're adjusting X to reduce its resistance, right? This will increase the current in the coil. Right? So that's the answer for that part there. What else we have to do here now? When the switch is closed, the reading on the ammeter is 1.5 amps. Calculate the resistance of the coil. Oh, this is a baby question, guys. All right, so V is equal to IR. All right, we want to work out the resistance in the circuit. So that's R is equal to V over I. The power supply was 12 volts. So this is 12 volts all over the current, which is 1.5. So therefore, this is going to be 12 divided by 1.5. So this is going to be 8 ohms, right? That's the answer there. Right, guys? So if you haven't done so as yet, please remember to hit like and subscribe, right? My new physics class for Form 4s will begin in August 2023. You can always send me a WhatsApp on this number here, right? It's not question 5, this is question 6. So this is the last question here, guys. Right? Last question. Figure 10 shows a vacuum tube with a radioactive source which emits alpha, beta, and gamma through an electric field. Right? What they want to know here. So describe the parts of, so they want us to describe the parts. Right? So let's start with the easiest one. So gamma rays, right? They are undeviated as they pass through the electric field. They are undeviated right? They're undeviated when passing through the electric field. Right? And the reason for that is that gamma rays have no charge, right? So you can even see that gamma rays are uncharged. Right? Because I've seen 2 marks here, so I probably should mention that, right? Let's talk now. So alpha particles are positively charged. So you're going to see that. Alpha particles are positively charged. Right? And are deflected towards the negative plate. Right, now when we say negative plate here, let's look at the diagram first of all. Right, so the diagram is the negative plate is at the bottom, so they're going to move, the alpha particle is going to move downwards, right? So you're going to say it downwards. Right, the next thing here, beta particles, so you're going to say beta particles are negatively charged. Right, and are deflected towards the positive plate. right? And because we're talking about the positive plate here on the diagram, that means that they're going to move upwards, right? Now I'm just putting all of these details here because I'm looking at the number of marks, right? So, right, so that's part A. Part B now, right? Now this is so funny. I did this with my Form 5 class literally the Saturday before you all had this exam, right? The same question, right? So we have an equation here representing a nuclear fission reaction. So this is a common nuclear reaction that we use, right? What do we want here? Calculate the total mass of the particles on the left and the total mass of the products on the right. So the particles on the left, right? So you have to cater for the uranium-235 and the neutron. So you're going to take this number and add it to this number here, right? So that's 3.902. 3.902 by 10 to the something, minus what, 27? Minus 25 kilograms, plus the mass of the neutron, which is 1.675 by 10 to the minus 27. So 1.675 by 10 to the minus 27. Right? That's the only thing on the left-hand side. So it's going to be 3.902 by 10 to the 25 minus plus 1.675 by 10 to the 27 minus equal. Now, I'm not going to round off anything as yet. So 3.91875 by 10 to the minus 25 kilograms. So I'm not rounding off anything as yet. The products now. When you go to the diagram now, sorry, the equation, you have barium, you have krypton. Now, some students might forget this, but you have 3 neutrons here. See this number 3 here? You have to cater for that. So the barium is this number here, 2.289 by 10 to the minus 27. 2.289. 2.289 by 10 to the minus 27. Right? Plus, so that's barium. We need to add krypton. So that's 1.575. 1.575 by 10 to the minus 27. Right? Plus, now you have 3 neutrons. So that's going to be 3 multiplied by 1.675 by 10 to the minus 27. Right? So let's see what we're going to get here now. So that's 2.289 by 10 to the 27 minus plus 1.575 by 10 to the 27 minus plus 3 multiplied by 1.675 10 to the 27 minus that. And I'm getting 8.889 by 10 to the minus 27. Right? Alright, so we have the mass here. So I guess the next thing they're going to ask us is the mass defect. Right, so the mass defect now, or the mass difference, all you're going to do, right, you're going to take the mass of the uranium-235. So that's 3.91875. 3.91875 by 10 to the minus 25. And you're going to minus the mass, the total mass of the products, right? Which is going to be 8.89 by 10 to the minus 27. 8.89. Sorry, 8.889. Right? Let me use the numbers from here in case I'm making a typo somewhere, right? So that's going to be 3.91875 by 10 to the minus 25. And you're going to minus 8.889 by 10 to the minus 27. And I'm getting this here. 3.83086 by 10 to the minus 25 kilograms. Right? So I normally tell my students, don't round off anything as yet, right? You can round out the final answer if you want. So now they want the energy release in the reaction. So E is equal to mc squared. So the mass that we just got, which is 3.83086 multiplied by the speed of light squared. Common mistake here is that students forget to square the speed of light, right? That's a common mistake. Multiplied by 3 by 10 to the 8, close brackets, squared, right? And I am getting 3.4 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Right? Let me just double check that answer though. Yeah, hold on there, right? I just realized I wrote something just now. Right, so this would have been by 10 to the minus 25. Multiplied by 3 by 10 to the 8 squared. So let me just work this out again, right? 3.830. So I'm getting around 3.4 by 10 to the minus 8 joules, right? All right, guys, so that brings us to the end of this June 2023 paper, right? Like I said, if you like my work, right, please hit like and subscribe, right? My new Form 4 physics class will start in August, right? So you can always send me a WhatsApp at this number, right? All right, guys, so that's it for me. This is Terry here. Take care, guys.